My background is actually not in medicine at all, but as Daniel said, it's in data science, or more specifically, machine learning. How many people are here sort of familiar with what machine learning is, have come across that idea? About half of you. OK. So maybe I should give a bit of an explanation of where machine learning comes from in order that we can understand what it is, and then we can talk about what we can do with it in medicine. So maybe the best way to describe machine learning is to go back to 1956, when machine learning was invented. So it was invented by a guy called Arthur Samuels, and he was an engineer at IBM. And he wanted to create a game, a computer program that could play checkers. So this is the computer he's trying to program to play checkers. Now, Arthur's problem is that he is not very good at checkers himself. So if you think about how do you write a computer program, you basically write a bunch of rules, or to be more specific, what are called conditionals, if-then statements. So how do you create the rules to describe how to be good at checkers if you're not good at checkers yourself? So what he tried doing instead was something pretty clever, which was he said, all right, why don't I tell the computer about all the different kind of axes on which one could play chess, the different decision criteria there are in chess, and then have the computer play against itself and see what happens. And so he had this computer play against itself thousands of times in 1956, and actually it got so good that it was able to beat Arthur Samuels at checkers. So the CEO of IBM went out to the markets and said, we now have a computer program that can beat its own creator at checkers. And IBM's share price went up 15% on that news. By 1962, this computer was able to beat the Connecticut state champion. So machine learning is this way of getting a computer to do something which either you don't really know how to do yourself, or you don't really know how to describe how you do it. So if you think back to 1999, this is what we all used to search the internet. And so a large team of human editors, as they were called, were literally paid to surf the internet. And as they surfed the internet, they looked for really cool websites, and then they put it into this taxonomy that was manually created. And then somebody came along with this crazy idea. And it replaced that entire team of human editors with a computer program based on machine learning. And this would try to figure out what you might be interested in looking at, not using people, but using an algorithm. And I remember when this happened, a friend of mine was actually creating a new startup to compete with Yahoo by creating a better team of editors. And I told him at the time, I think this is actually going to win. And his answer, as was most people at the time, don't be ridiculous, a computer program could never understand what people like better than people can. Well, we all know what happened. And today, machine learning is used all over the place to do these amazing things, like recommending what books you might like, as well as or better than your neighborhood bookshop. Figuring out who your friends might be. And I bet my friends are more interesting than yours. This is actually LinkedIn's recommendation system. Again, this is not something that anybody knows how to write a specific set of code programs to do, but using machine learning, LinkedIn and Facebook can actually figure out uncannily, eerily well who maybe you should connect to. And of course, there's Watson, which was able to answer questions like this one, not because anybody figured out the rules of the game of how to describe how to win Jeopardy, but because it fed it with lots of information so it could learn to play for itself. And so Watson is a good idea. In fact, Watson is a hybrid system which involves both machine learning and some traditional programming techniques. So Arthur Samuel had this crazy idea. In 1962, he made two grand predictions that nobody had ever made before. The first one was that one day, everybody would own their own computer. Secondly, he predicted that one day, people would not program computers on the whole, but would simply tell them what they want to do, and the computer would figure it out for itself how to get there. So my thesis is that, what on earth is that? My thesis is that computers, the fact that computers now appear on everybody's laps here is something which has happened. The fact that we still program computers on the whole in this very manual, arty way is something which is in the process of changing. So maybe if we switch across to my laptop for a moment, have some of you come across this website called Iodine? This is pretty amazing. So Iodine is a website which is applying some of this idea of doing a data-driven approach to medicine. And what they actually did was something fairly simple, which was they asked 100,000 people about their experiences with drugs. So using this system, I can type in any drug, like so. And it immediately tells me this is kind of the world as a real-time drug experiment. You can see what people are saying about their experience with Ritalin. And where it gets really interesting is I can drill down and look at, for example, OK, how well does Ritalin work for you? Yeah, somewhat to well is pretty common. Amongst 18 to 34, pretty similar. 35, 54, yeah, a bit more. But what's really interesting is that we look at this like hassle here. No hassle for young people, and actually a huge hassle for many older people. And you can start to learn about what's happening in the real world of using medication by drilling into the pure data rather than drilling into necessarily the underlying science of what we think ought to work. Perhaps this is a way of generating new hypotheses that we can then test in the lab. So there's been a lot of stuff happening in machine learning. It's actually impacting all of our lives today. It's certainly impacting medicine as well. This is an example that came out in Nature a couple of months ago by a guy named Hugo Ertz and his team. They're from Brigham and Women's. And they were looking at lung tumors that came out of an MRI. And they were basically saying, OK, well, normally when a radiologist looks at a lung tumor, they characterize it across maybe 2 or 3 axes. It's either there or it's not, it's big or it's small, maybe it's homogeneous or heterogeneous. They actually tried doing this thing called feature extraction, which is shown in this picture here. They looked at extracting 6,700 features for a tumor. And they discovered dozens of new clinically relevant features that nobody had ever come across before, simply by using this machine learning approach to see if they could identify new ways of thinking about tumors. And so as a result of this research, there's now all these new features which actually tell us a hell of a lot about the prognosis of a patient. It's not just in radiology. Exactly the same thing has happened in pathology. This was quite fascinating, actually. This came from a chap named Andy Beck. He was at Stanford at the time. He's now at Harvard. And he looked at breast cancer biopsy tissue. And he did something very similar to what Hugo Ertz did in what he calls radiomics, or in radiology informatics, which was he built lots of features. You can see the features in the bottom left-hand corner here. He again created thousands of features, about 7,000 features, using a semi-automated mathematical approach and a lot of domain expertise to build them, and then used a fairly simple machine learning process to try to find out which of these features was relevant in predicting the probability of survival after 5 years. 2 interesting things here. The first is this machine learning approach turned out to be more accurate than human pathologists at making that prediction. Secondly, when they drilled into that model, they discovered that one of the key reasons for that is that it used tissue which is not in the cancer, not in the tumor itself, but around the tumor, tissue which all pathologists were taught to ignore when doing this assessment. Because computers are not making assumptions based on what people have told them in the past, the computer was able to ignore that and discover actually the tissue around the tumor is critically important in looking at prognosis. A lot of people who are familiar with machine learning put up their hand at the end of my presentations and say, don't know about machine learning, it's kind of a black box, it doesn't really tell us what's going on, it just makes predictions. As you can see from the work of Ertz and of Andy Beck, this is the opposite of true. It actually discovers things that we didn't even know to look at before. It's much, much more than just a black box. So all of this amazing work in machine learning is then going to allow us to use big databases of holistic, of lots of different types of information much more effectively. So one great example, and I think Jeroen might be talking about it this week, is what Philips is doing, looking at putting together a huge array of different types of data, and this is just very recently announced. If you imagine with EMR and imaging and genomics and consumer-generated data all in the one place, machine learning gives us the tools to allow us to actually analyze that all together. So why do I know a bit about this machine learning thing? Well, it's because I used to be involved in an organization called Kaggle. Kaggle is actually the world's largest machine learning community. It has about 210,000 data scientists. I initially was actually the highest ranked participant in the competitions that Kaggle ran, and then became the president and chief scientist. So for a period of some years, I was lucky enough to basically speak every day to the world's best data scientists and the people trying to solve the world's toughest machine learning problems. This is an example of one, actually, that came from Allstate. Allstate put out to the internet about 100,000 insurance applications, and for 50,000, anonymized, of course, information about each of those applicants. And for about half of them, also released what the claim costs over the next year for each of those applicants was. And then for the other half, they basically challenged the people in the Kaggle community, can you come up with a model to predict the claims of this other half of insurance applicants? As this slide describes, in fact, the answer was yes, very much so. Within a day and a half, the best Kaggle competitor had beaten the model that Allstate's team of actuaries had developed over many decades. And after 3 months, they had beaten it by 270%. In fact, every single Kaggle competition, hundreds have been run, has always beaten the state-of-the-art best result from both academia and from industry. So by looking at Kaggle, I got this really interesting, unique insight into how to solve the world's toughest problems in ways that had never been done before. So in late 2012, something amazing happened, which was there was a competition for Merck where the winners of the competition created the best ever automated drug discovery algorithm in just 2 weeks. They beat everybody else in the competition, and none of them had any previous background in biology or life sciences or chemistry or pharma whatsoever. And they beat everybody else by a sizable margin. Now, how on earth could somebody do that in 2 weeks? We actually looked into it in some detail and discovered that they had used a technique called deep learning. It was such a big deal, in fact, that it appeared in a New York Times front page article some weeks later. This is the guy that led the team that won this competition, Geoffrey Hinton. And it's quite extraordinary to discover that there was a new type of machine learning algorithm which doesn't require any of that feature extraction we saw before. Remember the pathology and radiomics examples where they had to create features which were very specific to those domains? In this case, they didn't do any of that. They just took the raw data, and this system called deep learning automatically figured out these features. It actually turns out that this is being used very widely, and this New York Times article, as well as looking at Hinton's work, also looked at this guy, Rick Rashid, who was running Microsoft Research, and work he had used in applying deep learning to speech recognition. I'll show you the results of that work now, and if we could have the audio on for this section, please.
Now, the last step that I want to be able to take in this process is to actually speak to you in Chinese. Now, the key thing there is we've been able to take a large amount of information from many Chinese speakers and produce a text-to-speech system that takes Chinese text and converts it into Chinese language. And then we've taken an hour or so of my own voice, and we've used that to modulate the standard text-to-speech system so that it would sound like me. So what you see now is the result of that change. I'm speaking in English, and hopefully you'll hear me speak in Chinese in my own voice. Again, the results are not perfect, There are, in fact, quite a few errors.
结果并不完美。他们仅仅想复盘错误。
There's much work to be done in this area.
在这方面有。
So that transcription you saw in the top left was also a deep learning algorithm creating that, and as was the Chinese text in the top right. So here's one algorithm which can automatically discover drugs and transcribe the human voice and do translation. It actually goes back some time to 1995. This was actually from a website from back then, showing how handwritten numbers can actually be automatically recognized. And this system was used to read about 15% of the checks in the US. Really reminds me of Peter Diamondi's description of exponential growth. This deep learning thing has been around for decades. And it's just started to get to the point, 1995, it got to the point it could read numbers. And then suddenly, 2012, it's the point it can discover drugs and do real-time voice translation. So I started really looking into it at that point, and I discovered that 1 year earlier, in 2011, there was a very small, little-known competition in Germany involving looking at traffic signs with machine learning. When I looked into this, I discovered something amazing, which is that the top-ranked machine learning algorithm for looking at traffic signs turned out to be more accurate, in fact, twice as accurate as humans are at recognizing traffic signs. So in 2011 was actually the first time a computer was shown to be better than humans at looking at stuff in at least one small area. A lot has happened since then. Google came out saying that they had a deep learning algorithm watch a week's worth of YouTube videos for about a month. They analyzed it with 16,000 computers and discovered, once they looked inside, that the system had automatically discovered the concept of a person and of a cat without being told anything about these kind of ideas, as well as about 600 billion other concepts. Also in 2012 was the first time that deep learning was used to understand arbitrary images in something called the ImageNet competition, which tasks people in the competition to look at about 1.5 million images and figure out what they're a picture of, including like what specific dog breed is it, or what kind of algae is it, or what kind of mushroom is it. As soon as that happened, the state-of-the-art result was basically beaten by double. It had been pretty flat for years before that. And so at that point, in fact, pretty much everybody in computer vision started looking entirely at deep learning. And as a result, the best in class for computer vision accuracy has improved by twice the accuracy every year. And in fact, in the last 5 years, we are now about 10,000 times faster and about 10 times more accurate than we were 5 years ago. It's also being used for language. A very complex to understand sentence like this, that red dot at the top says negative sentiment. Computers are now able to read sentences like this one and understand what they're about and what they're saying about that thing. And so it's now being used for medicine. Here's an example in pathology of using deep learning. The little green areas are areas of mitotic activity, a key driver of diagnosis and understanding breast cancer. A deep learning algorithm was able to look at these slides and without any kind of specialist domain knowledge, any kind of special feature extraction, written by somebody with no background in pathology at all, we're able to create the world's best ever algorithm for identifying these mitosis areas, about as accurate as a human pathologist. It's also been used for things like neuron segmentation. The world's best neuron segmentation algorithm now is better than a human and was created by people with no background in the field using entirely these deep learning algorithms. So I want to show you some actual demonstrations now of some actual results which have just recently come out. I'm going to start with one that has come from Baidu. So Baidu is kind of the Chinese Google. And they actually have an online demo of a deep learning system, which, based on the sample images, seems mainly to be about trying to find attractive women. I will use it for a different purpose. So I'm just going to grab an image off my computer. So this image has no text or context or anything else attached to it. And it will upload this to the Baidu deep learning system. and come back and say, so I actually do speak Chinese, so I can tell you this says this is a golden retriever. This is various different types of golden retriever. So it's figured out what it's a picture of. But really interestingly, it's also got something here saying similar images. And look what else it's done. It's found other pictures of dogs with a similar background, with a similar composition, a similar head angle, and even some of them with their tongue sticking out. Imagine if that was a liver radiology image instead of a dog. And imagine it had been trained to recognize other liver images which were similar in terms of their prognosis or likely interventions. You could actually find other cases that are going to teach you about what's going to happen to this one. Or let me give you another example. This demo is actually developed by us, and this combines deep learning for sentences with deep learning for images. I can start searching for something, and you can see as soon as I start typing, it starts finding things like that. Now notice these pictures do not have any text or anything attached. They're just images. So the computer was able to figure out these pictures of a bird. It can do grammatical things like plurals. But what's really cool is because we can now use deep learning to analyze whole phrases and sentences, it's actually able to find pictures based on a full description like that. Again, imagine this in medicine. Imagine that I was typing in a sentence and it was able to find things not based on how the radiologist had described them, but based on the full detail of what's in the image, including the thousands of different ways of thinking about it that Hugo Ertz, for example, showed in his radiomics study I showed you earlier. So that's all pretty amazing. But I do want to show you one more thing. If we could jump back to the slides, please. I want to talk about how we can build these kind of systems. So what I did was, after realizing everything that's possible with deep learning, and also the huge need in medicine, I decided to start a new company focused on pulling these two things together. This is what Enlitic is. It was only launched 3 months ago, very new company. And what we're actually trying to create is a system that allows us to build a new diagnostic tool within a couple of days. Currently, it takes a team of people about 5 or 6 years. And I want to show you now how we're going to do that. Now, this is an actual example. No one's ever seen this before because this was actually only... We finished creating it this morning, and one of my engineers sent me the video just a couple of hours ago. So this is the first time this has ever been seen, and this is actually research that has just come out of our lab over the weekend. We finally finished it. I'm not going to show you it with medical images. I'm going to show it to you with cars. Right? But the reason for that is to make this much more interpretable. So imagine in this situation that you've been tasked with building a system that can recognize what angle a photo of a car has been taken from. So we start out with, in this case, this is all real time, about 1 million cars. And we're going to look at, just for the purpose of making it easier to see, we'll look at a few thousand of them on the screen at once. And we want to figure out what angle are they. So we use a deep learning algorithm to immediately try and find if there's any structure in these pictures. And you can see, without any kind of training, these are totally unlabeled, it was able to find out, oh yeah, some things look at tires, some things come from a kind of a corner angle. There are other things which, when we zoom in, we can see, oh, there's kind of a mixture of backs and fronts there, so that's a little bit harder to pull apart. So what we can then do is, this is actually in what's called deep learning space. It's about a 16,000 dimensional space. We get the computer to rotate it through that 16,000 dimensional space, trying to find other interesting areas of structure. And as we do, it automatically identifies, oh, here's some areas where there are some more side angle shots, for example, but here are some wheels in a different place. So let's now start teaching the system about what we're looking for. So we say, okay, we're interested in finding things that are wheels, and we're actually also interested in finding things which are kind of an angular shot. You can imagine we were doing this, looking for stromal cells or epithelial cells or mitotic cells or so forth. It's the same basic idea. So now we go down and we try and find some examples of other things that it was able to identify. Now down here, we haven't quite done a great job. We've got both fronts and backs. So for now, we'll just say, okay, fine, fronts and backs. And so we're trying to teach it as much as possible about the things that we're interested in looking for. So finally, oh, here's some seats. So let's tell it that, yeah, we're interested in separating out seats as well. So we started out with this 1 million totally unlabeled car pictures. And we've got to a point now where we've labeled, a couple of hundred of them. Oh, here's one more set that perhaps we can do here. because these ones, here we go, here are the sides of some. So let's tell it also, yeah, we're interested in recognizing the sides of cars. So now we've labeled about a couple of hundred, and we run the deep learning representations through a different machine learning algorithm, which is called a random forest. And that takes about 15 seconds to run, so that bit we're going to skip over. So 15-second passes, and it's done. Now, what it's now done is it's re-shown us this, and it said, OK, I've used your tips about what you're looking for to automatically separate this out. So now you can see I've still got my tires. And in fact, you can see, as my engineer here is zooming in, if you look as he zooms in here, it's actually labeled them. You see it actually says on each one of these, angle, 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 for example. There's actually a little bit of statistics on the right-hand side cropped out that shows that it's successfully labeled about 1/3 of the million images already. So now we can ask the computer to rotate it through those 16,000 dimensions and identify a new projection which might show new interesting information. And lo and behold, it has. It's found a section here which has got just the backs of cars. So we could now use that to basically just select that group, and we've now taught it about, iteratively, something else new that we're interested in showing. So you can see there's no programming involved at all in this system. You can basically use this, a pathologist or a radiologist, anybody can use this to interactively identifying interesting diagnostic tests. It takes about another 4 minutes, which we aren't showing the rest of it, to end up with something that's about 90% accurate. Starting out with nothing but a bunch of 1 million images. So this is kind of the future, we think, of how medical tests could be created. And one day we hope to create from this true data-driven medicine. Thanks very much.